Hey, in this tutorial we're looking at section 14.3, which is the distribution of p hat. Okay, so p hat is called the sample proportion, and p hat is equal to the number of successful outcomes in the sample over our sample size. P hat is used to estimate a population parameter. Okay, the larger the sample size, the better the estimate of the population parameter. Okay, so when we talk about repeated sampling, okay, p is the proportion of successes in our population. Q is 1 minus p, or the proportion of failures. N is our sample size. X is our number of successes in the sample. And p hat is equal to x on n. So the number of successes over the sample size, which is what we had a minute ago. And this will vary with each sample. Okay, so as you can see, this is actually really a binomial situation. Okay, with p, 1 minus p, our n's and x's and such. Okay, so what we can do, okay, is we can do a bit of sampling distribution of p hat. Okay, so for this, if we had 20 bowls, 5 were red, 15 were blue, then the number of ways of selecting the 5 bowls is 20 choose 5, which is 15,504. Okay, when we select our samples, we could get 0, 1, 2, 3, 4, or 5 red bowls. Okay, so we could generate this table here. Okay, so we could say X is our number of red bowls. Okay, the population proportion, okay, is going to be, well, 0 if we choose 0, 1 out of 5, 2 out of 5, 3 out of 5, 4 out of 5, or 5 out of 5, or just 1. Okay, so the number of samples, okay, that would have each of these proportions can be worked out by going 5 choose 0 times 15 choose 5, meaning that we'd have 3,003 times, okay, or ways we could sample and get no red ones. Okay, 5 choose 1, 15 choose 4 gives us 6,825 different ways of selecting just one red one. 5 choose 2 times 15 choose 13 gives 4,550 for 2 red bowls. Okay, 5 choose 3 times 15 choose 12 gives us 1,050 for choosing 3. 5 choose 4 and 15 choose 1 gives us 75 for choosing 4 red bowls, and 5 choose 5 times 15 choose 0 is 1, because there's only one way of selecting the 5 red bowls. Okay, we can do our relative frequency here, okay, which is just these numbers here divided by our 15,504. Okay, and our relative frequencies can become our probabilities in the distribution table. Okay, so we can have our population proportion, okay, by their relative frequencies, which is basically the probability of getting these proportions. Okay, and we can, if we find our expected value of p hat, or our mu, it becomes 0.25. So if we go 0 times that, plus this times this, 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 okay, to add them all together, yeah, okay, to find our expected value, it actually becomes 0.25, which you know there is, because there's 5 out of 20, which is 0.25. So you can see that it actually does do a good estimate of what our actual population proportion is. Okay, what this means, okay, is that mu hat is actually equal to p, our probability of success, which is our 0.25, and sigma of our population proportion is equal to the square root of p outside of 1 minus p divided by n. Okay, this also implies that large samples are normally distributed, because we've got a mean and standard deviation. We wouldn't get that if it wasn't normally distributed. Okay, so we'd expect a normal distribution with this stuff. Okay, so we can also say that a sample is large if n times p is larger than or equal to 10, or n times q is greater than or equal to 10, and that 10 times n is less than n. Okay, so we're basically saying we want to be, this one's really saying that our sample size needs to be a tenth of our population size, something along those lines. Okay, so we can have a look at our worked examples for this section. So we've got worked example 6. Okay, consider a population size of 1,000. Well, that's going to be our capital N equals 1,000. Okay, and a sample size of 50. So that's our little n equals 50. Okay, we know that p equals 0.1. Okay, would this still be a large sample? If not, how big would the sample need to be? Okay, so we have a look. Okay, is 10n less than or equal to n? Okay, well, we go 10n, well, that's going to be 10 times 50, which equals 500. Okay, so yep, that's satisfied. Okay, and then we go, is np greater than or equal to 10? Okay, well, we go np, well, we go p is 0.1, n is 50. Okay, so 50 times 0.1 equals 5. So that one's not satisfied. Okay, so that is not a large sample. Okay, and so we know it's not. So now, if not, how big would the sample need to be? Well, we need np to be at least 10. Okay, and we know that p is 0.1. So 0.1 times n equals 10. So n equals 100. Okay, so we need to check our other conditions if n was 100. Okay, so if we times that by 10, okay, we're the same as n, so that's fine. We go n times q, well, n times q is 0.9, because it's 1 minus p. Okay, so that's our 100 times 0.9, okay, and that equals 90, which is greater than or equal to 10. Okay, so our n of 100, okay, would be a large sample because it satisfies all our conditions. Okay, have a look at work example 7. If n, capital N, is 600, so our population is 600, and our sample is 60, okay, and our p is 0.3, find the mean of the distribution. Well, mu p hat equals p, so our mean is equal to 0.3. And for part B, find the standard deviation of the distribution correct to 2 decimal places. Okay, well, our sigma p hat equals the square root of p outside 1 minus p over n. Okay, so that means it's the square root of 0.3 outside of 1 minus 0.3 over n, which is 60. Okay, which gives us 0.06. So that would be our standard deviation for the distribution. Okay, so that's all there is in terms of worked examples. Okay, so I know this is pretty new stuff and we haven't really seen a lot of it before. Okay, so just make sure that you have a look at those worked examples, okay, etc. Okay, and yeah, try your best to get through the questions as best you can, really.